Something is happening there.
You know, Professor, if this Zoom thing is giving you trouble, then I can just go and watch recorded videos later.
Yeah, I think it is, but I'm just going to try and do one more thing for you, and that's it.
I wouldn't want to waste the lecture time.
Yeah, I understand. Yeah, the most I can do, I think, is going to be that. So whatever happens, happens. Okay. Partial of f with respect to x, that means we're holding the y to be constant and taking the derivative. That's a first partial derivative. We're looking for second partial, all the possible second partials. So we're going to take the derivative with respect to x first, then we can do x again, and that would be like a second derivative. Or we could do partial of f with respect to x, then y. We could do the partial of f with respect to y, then y. And then we could do the partial of f with respect to y and x. There's only 4 possibilities there for the second partials. So let's do these one at a time. And to do these, I think the best thing to do is first start off by finding the partial of the function with respect to x. Let's figure out what that is first. So we look at this thing, and we are going to treat all of our y's like constants, and then treat our x's like variables, right? And then take the derivative. So the derivative here of the first term is going to be 2x. And then the derivative of the second term is 0 because, again, y is a constant. So this is all just some big constant. And then on this one, minus 10x cubed y to the second. Again, because the y is a constant, y squared, we're just going to imagine that as being a number. I'm going to put it next to the 10. So I'll write minus 10 y squared. That's my constant on this term. Now I need to take the derivative of the part that has x in it. So a derivative of x cubed would be 3x squared. And clean that up just a little bit. 2x minus 30y squared x squared. Any questions on that? Yeah, you're okay? Yes? All right, I'm going to use that in a minute. Let's now get the partial with respect to y. If we do the partial with respect to y, treating x like the constant now, that goes to 0 when I take the derivative. On this term now, I have to do the power rule. So that's going to be 20y to the 4th. And now on this last term, it's kind of a reverse of what we just did. The x cubed is our constant, so we're going to just attach it to the negative 10.
You actually wrote y to the 5th.
Why did I write that? I think I said y to the 4th, didn't I?
You did say right.
Okay. I've been doing that today. I've been writing nonsense, so y'all pay attention. I've been doing that several times today. So negative 10x cubed, and now I need to take derivative of the y squared, which is 2y. And then clean up again. Okay, there's your partial of f with respect to x. There's your partial of f with respect to y. Now to get these partials, what we do, and remember when you read this notation from last class, when you read this notation, you always start with that derivative first, and then you move on to this one next. So this is the first thing you do, and that's the second thing you do. So first we took the partial of f with respect to x. That's the top one. And now what I want to do is take the partial of that with respect to y. So I'm going to write it this way. I'm going to take the partial with respect to y of this. Oh, sorry, with respect to x again. Sorry, we're going to x. Whew. Okay, so partial with respect to x of the partial with respect to x. So treating x like our variable and y like our constant, the derivative of 2x is just 2. The minus 30y squared is all one big constant. So I'm going to bring it with me. And then the derivative of x squared is 2x. And that cleans up to be 2 take away 60. It doesn't matter what order we put those in. Y squared x. Okay, now we move on to the next one. Here, we're going to take the partial with respect to x, which we've done, then the partial with respect to y. So I want the partial with respect to y of what we already did. Okay, and now when I do this with respect to y, x is like a constant, and so the derivative of that would be 0. Over here, the negative 30x squared is the constant, right? So all I have to really consider is the y squared, and the derivative of that would be 2y. So I'm going to do this all together in one piece. I would get the 0 out front, right? This would give me a negative 60 y squared times x. So I went ahead and did that all. Jesus, Robert. Thank you. Questions? All right, partial with respect to y, so that's this bottom one. And then we're going to do it with y, with respect to y again. So the partial with respect to y of, today is very much just mechanics, making sure we know how to do these things, and then we'll apply them to something later. We just want to make sure we have the mechanics of this down. All right, so I want the partial with respect to y of this. So I'm just going to use power rule again there. So that's going to be, let's see if I can do this without screwing it up, 80y cubed. And then here, the minus 20x cubed, that's all a constant. And so I only have to take derivative of y, which is 1. So we should just get minus 20x cubed. All right, one more. Partial with respect to y then x, right? That's the last one. I'm going to leave this one on the board. I'm going to erase this one. We want the partial with respect to y then x. That's our fourth one. So that's the partial with respect to x of the one we already did, which was this one, partial with respect to y. And if I take the derivative of this with respect to x, that term goes away because y is a constant. And then here, the y is a constant, minus 20 is a constant, so I'm only taking derivative of that, which means the 3 will come out, right, and give me a negative 60. That'll become an x squared. And I'll still have the y there. So negative 60 x squared y. Yes?
So does that make higher order partial derivatives associative? I don't know if that's the right question. Because
So you're recognizing these are the same thing, right?
Yeah.
Okay, so we have a theorem next which will tell us when this will happen. Okay, do y'all notice that these two are the same answer? Yes.
So, quick question. For this derivative of y, then derivative of x, for the Leibniz notation of it,
Yes.
where you got the d over dx,
Yes.
if you were to write that original portion of d over dx dy, which one would be the first, which would be the second?
Okay, so if I wanted to do this, this is the same as taking the derivative with respect to the derivative of, f. Well, you want it as an operator form, right? Not naming it. So it would be like partial with respect to y, then inside the partial with I did this backwards. Jesus, I think I need to step outside and just like start over today. This is the notation. I think that's what you're asking. This says with respect to y first, so you do that there first, right?
Yeah.
And then after you're done with that, you take the partial with respect to x. So it'd be on the outside like that.
Gotcha. So in the notes, couldn't we write it as a single fraction? Yeah.
Yeah, it's all right here. Yeah, it's all here.
Cool. So you'd write the second one second. Gotcha.
Got it? Okay, so now the theorem. Okay, noticing that these two partials were equal, right? So Clairaut's theorem says that if you're given some surface, f of x, y, right? As long as that f is defined on some disk that contains some point. I don't want to get too deep into this at all, other than to say, I'll try and draw a picture of what's happening here. We have a surface up here, right? This is our f function. right? It's saying if we're looking at some point, remember the domain of this function is on the ground, right? It's a point in two-dimensional space down here on the floor. That's our x naught, y naught. That gets plugged into the function and we land somewhere up here on that surface. This theorem says that as long as f is defined on some disk D that contains this point, so if you have a little disk here that goes around this point, and imagine mapping that up into here, that doesn't necessarily need to be a disk. It can be moving around like kind of wavy up there, all right? It's saying if our function is defined on some disk that contains the point x naught, y naught, and when you do these second partials, they're both continuous on that disk. That means that when we take a look at those partials, we don't have any points where it's undefined. Maybe like division by 0 or square roots of negatives or something like that. It's not happening anywhere in this disk. Then we can be guaranteed that the partials will be equal to each other. The order here does not matter. All right? So the way I look at it is this. On the problem we just did, when we looked at those two partials, those were nice little like polynomials, weren't they? It just had like x's to powers and y's to powers. I would never have division by 0 or roots of negative numbers or trig functions that involve domain restrictions. So as long as there's no problems, we should expect that we will always have those two equal to one another. All right? Okay. For the next one, we are going to, this would be like a Cal 1 class. If you were asked to find like the fourth derivative of a function, that's what this question is like. We're asking for the fourth derivative of a function, but because it's a function of two variables, I can kind of tell you what order I want you to go in. Okay, so I want you to go with respect to x first, take that answer, then go with respect to y, then that answer with respect to y again, then that answer with respect to x. So when you read this notation, like I said, it's left to right. All right, so let me first find the partial with respect to x. Okay, with respect to x, it's going to be 2x. Derivative of that is 0. Isn't this the same problem from earlier? Minus, this is 30, x squared, y squared. Okay, that's the partial with respect to x. Now I'd like to take the partial of that with respect to y. Now we did that already, right? And we got negative 60 x squared y. That work we've already done in the previous problem, didn't we? But now I'd like to go with respect to y again. So the partial of this with respect to y would be what? Negative 60x squared, right? Because y is the variable, the negative 60x squared is the constant. So now it's this. And then I want to go the partial with respect to x of that, which just power rule, right? So negative 120x. We're done. So again, this is more mechanics. We're not right now trying to figure out, well, what is this? Like, what does that represent, right? We're just making sure we know the mechanical part of taking partial derivatives. Next one. What do we want? We want partial with respect to y, then x again, right? So partial with respect to y, then x again. Well, look, didn't we already do this? We did that, didn't we? The first two, we did that already. And that was this one, wasn't it? Because they matched. So I'm not going to go through that work again. That's negative 60 x squared y. And now I'm ready to answer this question. What's the derivative of this with respect to x? Right, that's what we're doing now. First y, then x. We did that already. And then now with respect to x again. So we get, what? Negative 120 xy. These are not the same, right? Yes?
I think that was Georgia. She said that she couldn't see your video, so she just
Yeah, I tried. I gave it the best. One of your classmates was out sick and wanted to still participate, and so I tried to get a live thing going, but it didn't work out. I think it bogged my computer down too much to try and have, like, feed this and get that, and yeah. Okay, it's being recorded. All right, we good? Questions? All right, now this is a kind of a, we're not going to get into a deep study of what Laplace equations are and where they're used and how they're used and, you know, do an application. This is just purely to define what a Laplace equation is. And then we're going to do an example. So a Laplace equation is any equation that satisfies that condition right there. This notation is used mostly in physics, but this is notation I was just using right now. I like this notation. What this says is, look, if you ever have some function, I'm going to call it, instead of f of xy, I'm going to say u of xy. So you can say the name of this function is u instead of f. So I've got this function u. It's a function of two variables, x and y. A Laplace equation is this equation right here. All it is the partial of this function with respect to x twice plus the partial of this function with respect to y twice. And then you set that equation equal to 0. And that's called a Laplace equation. So now what I'm going to do is give you an equation, and I'm going to ask you whether or not this equation, whether or not this function satisfies the Laplace equation or not. Does this satisfy it or not? I accidentally left it off here. I'll type it back in. Does this satisfy the Laplace equation? So let's look at that function up there. What's the partial of it? Well, let me write down what we're trying to check. Right? Is this true? Right? That's what I'm checking. Is this true? And not only is it true, I mean, is it true always? Does that equation hold all the time? Right? That's what we're checking. So that means I'm going to need some second partials, right? So let's get those over here. Partial of u with respect to x, 3x squared plus 3y squared. All right, that's our partial with respect to x. You all agree or not? Yes? Anyone have a question on that? Do you all feel pretty comfortable with this idea of partials? Like taking the partial, the mechanical process? Okay. Now I'm going to take the partial of that with respect to x again. So that's going to give me 6x. And that's it, right? 6x. Okay. Now let's take the partial of that with respect to y. That should just give you 6xy. Because this is treating that like a constant in the partial with respect to y. So we're just taking derivative of that with respect to y, holding the x constant. And now we do the partial of that with respect to y a second time. And we get 6x. And now we take those two answers and we plug them in over here and see if it's true. So does 6x plus 6x equal 0? Well, does 12x equal 0? No, not always. Now there is a value of x which it does hold, right? There's only one value that this holds, right? But generally it's not true. So this is not true generally. So the only point at which this satisfies the Laplace equation, right, is when x is 0, right? That's the only place. And if x is 0, then what is, right? If x is 0, then what is your function, right? It's just a 0 function. It's pretty boring, right? So functions that satisfy the Laplace equation all the time are used in, I put it here, like the heat dynamics, fluid flow, electric potential problems. How many of y'all have seen Laplace yet? Anyone seen Laplace yet? A little bit. I mean, normally you have to have seen like Cal 3 to do Laplace because you need to know what partials and how to do partials. And All right, moving on. All right, I wanted to remind you before we do this, I wanted to remind you of implicit differentiation from Cal 1 before we get into this. So recall, let's say you're given something like x squared plus y squared equals 9, right? You're given an equation that has x and y in it. And you're asked to find, let's say, dy dx, all right? So I'm going to put over here, this is Cal 1. Okay, this is where you would have seen this, all right? So you're asked to find dy dx. Now you could go try and solve this for y, like move the x squared to the other side, take the square root. The problem with that is if you take the square root, you're going to get a plus or minus, then you have to look at two different scenarios. So in Cal 1, we learned to use implicit differentiation. So with implicit, what we do, oh my gosh, this day is just turning into implicit differentiation. So I will take the derivative with respect to what on both sides of this equation? Y'all remember from Cal 1? In this particular case, with respect to x, because what am I looking for? dy dx, right? So I take the derivative with respect to x on both sides of the equation. The left side is x squared plus y squared, and then this here is 9. So now on the left side of the equation, we have two terms, right? Added and subtracted, we take derivative of each one with respect to x. So I take derivative with respect to x of x squared plus the derivative with respect to x of y squared, and then equals, well, the derivative constant is 0. Hey, and guess what? I don't care what math class you ever take in the future. Derivative constant is always 0. It's never going to change, all right? So that's 0, regardless of what derivative we're taking. And then on the left side, this is just 2x because we're differentiating with respect to x. So the left side becomes 2x plus, now this was the one that my Cal 1 students always struggled with, because when you're taking derivative of y squared with respect to x, you first have the power rule, right? So you get 2y. But then students forget, after you've done the power rule, you then have to come in here and take derivative of y, the base. And the derivative of y with respect to x is not 1, right? It's dy dx. So you get dy dx here, and then equals the other side of the equation. And then what you do is just move things around, right? You move that to the other side, divide by 2y, and you isolate dy dx. That's Cal 1. That's implicit differentiation in Cal 1. That's not what we're about to do. We're about to do implicit differentiation, but now we have an equation that has more than just x and y in it. It's going to have x and y and z. There's if you don't remember, in Cal 1, the reason why we brought implicit differentiation in is because there are some equations that you cannot isolate x or y. Like you cannot get the x or the y by itself. An example of that would be this one. This is a very simple one. If I give you that, there's no way you can isolate y. You can't get y by itself in terms of just x. So you can't get like all y's on one side and x's on the other. It's impossible to do. But there is a graph. If we graph that on Desmos, there's a graph, and that means there's tangent lines. And so implicit differentiation is what we use to find dy dx, all right? So it was useful in Cal 1. Here, same sort of story. We're going to have an equation here. And this equation, x cubed plus y cubed plus z cubed plus 6xyz equals 1. That is an equation containing 3 variables, right? It's an equation containing 3 variables. And if it's an equation containing 3 variables, then I can look at it as a surface, right? We've talked about this already, right? Equation containing x, y, and z should be a surface. And so if I have this surface, I want to be able to look at the z as being I would like to get my z to be some function of x and y, so actually I can see this surface. But I may not be able to solve that for z easily, right? I may not be able to. But I still want to know what the partial is with respect to x and with respect to y. So we're going to try implicit differentiation and see how it how it differs from what we did in Cal 1. So let's start with part A. Okay, so for part A, what I'm going to do is I'm going to take that equation and I'm going to differentiate both sides, partial derivative, right, on both sides with respect to x, because the denominator is with respect to x. So watch me write it down. I'm going to take the partial with respect to x of the left side. Now when we're doing this, please do not lose sight of last class. Last class we said when you're taking a partial of when you have a function of two variables, when you take a partial with respect to x, you're treating y like a constant, right? And when you do a partial with respect to y, you're treating x like the constant. So when I'm doing this right here, this is telling me, right, that y is a constant as I continue to do this, right? It's telling me y is going to be treated like a constant as I differentiate on both sides, right? All right, so let's do this. What's the derivative of x cubed with respect to x? It should be what it's always been, right? 3x squared. Okay, plus now the derivative of y cubed, well, y is a constant, so that's 0. Plus, okay, this is the part that is kind of like in that previous problem. This is the part that we have to be careful with. What is the derivative of z cubed? Well, first, power rule, right? 3 comes out. Do you? Z depends on x and y, right? So we are going to bring the 3 out, z squared times, now chain rule, take the derivative of what's here, right? Which is, it's the derivative of z with respect to x, but it's a partial derivative, not a traditional derivative. I have to use the partial derivative notation. So I'm going to have here next to this partial of z with respect to x. Well, look, you should be happy to see that, right? Because that's exactly what we're looking for, right? That's what we're trying to solve for. So it's good to see it show up, or I'll never be able to solve for it, right? All right, I'm done with the first 3 terms. Now, this. You have to be extremely careful because the y is a constant, right? But the x is not a constant, and the z is not a constant, which means I'm going to need the product rule if I differentiate that. Let me do it over here. I'm going to kind of rewrite it. I rewrote it intentionally. I put the 6 and y next to one another because the y is a constant, right? So I'm treating y like a constant. I'm just going to put it next to the 6y. I mean, next to the 6 to get 6y. Right? That's what this is? Mm-hmm. Now, we know that when we differentiate, constants will just come for the ride, right? They just come. So I'm going to just kind of ignore that. And I'm going to do the product rule on this. All right? So let me start writing it in here. Plus, okay, here's my 6y. And now I'm going to put a parentheses so that I can do that product rule on the x and the z. So if I do product rule there, the first thing I do is I take the derivative of x with respect to what? X. What's the derivative of x with respect to x? 1. Times, now this one z, plus, now we take the derivative of z with respect to x, right? That's a partial, so that's partial z with respect to x, and then finish off the product rule times x. And then that all equals 0, right? Who has a question about that? Now, I'm not done, but the rest is algebra that I'll leave to you. What you would do now, you could ignore that 0. What you could do now is try and get partial of z with respect to x isolated on one side of the equation. So to do that, I would have to distribute this through. and then move all my partial z with respect to x's to one side, everything that wasn't to the other, right? That's just algebra. And then you will have solved for partial z with respect to x. All right? Now, let's do the same problem, but let's now find the partial of z with respect to y. So what that does is that changes this to, we're probably going to get a different answer, right? So let's see. So changing this now to y, changing that to y. Now x is a constant, right? X is a constant. So when we take this derivative here, this one is 0, right? Because x is a constant, so derivative, that's 0. Plus, now here we have to use our power rule because y is our variable, right? So it's 3y squared times chain rule. What, right, the power came down first. Power, that to the second, then derivative of y with respect to y, right? Which is 1. So we don't really need anything else there. Plus, now the derivative of z cubed. Z is not a constant. Z depends on x and y, so that's going to be first power rule, 3z squared. But chain rule says now take the derivative of the base, the derivative of z, with respect to y now this time, right? Not x. And that will be a partial. Anytime you're holding a, I should have put y there, sorry. Anytime you're holding a variable constant, right, you're talking about a partial derivative. If you're holding one of your variables constant, then it can only be a partial derivative. All right, boom, boom, boom. Now, getting to the next piece. Again, product rule again, right? Product rule here. But this time, because x is a constant, the 6x, I can leave it like that out front, and then give myself some room for the product rule between the y and the z. There's my product. So I'm going to just use product rule. Derivative of y with respect to y would be 1 times z, plus now the derivative of z with respect to y, which is a partial again, times y. We're done differentiating the left side, equals 0. Oh, I forgot that bonus question. I think I have 3 solutions. I said first 3, right? I've got 3 solutions. 3 solutions to the first one, and then the second solution I only have one. The second problem I gave, only one person has gotten. So, just letting you know that it's still open. The second part of the bonus, the second one I asked about, only one person's got.
There was a second part?
Read the email.
Oh.
Yeah.
Can we
Yes.
talk about it after class then?
After class we can talk, depending on time.